So a basis for a subspace is a very important concept in linear algebra. You have a space, and you want to be able to have a basis for the space because that would allow you to take any vector in the space and write it as a linear combination of the basis vectors. Okay, so everything is basically represented. And you learn that different subspaces can have different bases. And sometimes one basis is more convenient than another basis, depending on the application. Like, for instance, a crystal lattice problem, it might be better to have a basis that isn't the standard basis, depending on the types of, well, depending on how the molecules are structured, so to speak, or the lattice is structured. So in the introduction here to section 4.7, they give you a vector x, and they have two coordinate systems in figure 1. Coordinate system, so you see the vector x in both pictures, figure 1a and b. The vector x is in the same spot. It's in the same spot in the picture. Okay? But the coordinates for the vector x relative to the, or with respect to the basis b, are 3, 1. So the picture on the left, if you start from the origin and you move 3 units in the 3 b1 units, and then 1 b2 unit, you arrive at the vector x. Okay, so the coordinates of the vector x relative to the basis b are 3, 1. But to the picture on the right, the vector x, if you use the basis vectors c1 and c2, well, from the origin, if you move 6 c1 units, and then from there move 4 c2 units, you arrive at the vector x. So the coordinate vector of x relative to basis c is equal to 6, 4. Now, are there any questions on that? Are there any questions on that? Who's feeling reasonably comfortable with that? Okay, very good. Very good. Excellent. Excellent. Thank you. Okay, so now and you've seen coordinate vectors relative to bases before. You saw that in section 4.4. But where the sort of the new thing in section 4.7 is that we want to have a connection between the two coordinate vectors. Okay, we want to be able, I want to say this the right way. I had a nice phrase in the book for this. We want to be able to, hold on. Let me just see here, one moment. We want to see how the two bases are connected to each other. Okay. So if you wanted to go from one basis to another basis, or from that other basis to the original basis, you need a transitional matrix, and we want to find that matrix. Okay, that's called your change of coordinates matrix. Okay, so there's a theorem here. Let me just find it here. Yeah, theorem 15. Okay. That says, make that a little bigger. If you have let's suppose you have two bases for a vector space V. Okay. And you want to, like you have coordinates of the vector x relative to the basis B, but now based off of that, you want to find a matrix P, which is a change of coordinates matrix from the basis B to C, So you could figure out the coordinates of the vector x relative to the basis c. That's what this first statement is. You have a coordinate vector of x relative to a basis b, and by multiplying it by a matrix P, we get the coordinate vector of x relative to the basis c. That's called your change of coordinates matrix from basis B to basis C, that matrix P. And it turns out that the columns of that change of coordinate matrix just consists of the basis vectors, the coordinate vectors of the basis vectors of B relative to the basis C. That's what they're saying in number 5. Okay, so, or yeah, that 5 part. So the matrix, the change of coordinates matrix from B to C, okay, well, I mean, basically what I just highlighted there is what I just had mentioned. You're going from one set of coordinates to another set of coordinates, and that's very important. One of my colleagues, actually, Dr. Boudre, said this is absolutely important for some linear algebra applications. And pictorially, this is really the scenario that you're doing right here. You have this coordinate vector, you have this vector x in vector space V, and you're trying to relate the coordinate systems with respect to basis C and a basis B. Okay, you're trying to relate the coordinate systems between basis B and basis C. So let's look at an example. Let's look at an example, and so you can see how this works. Okay, let me give you a moment to copy this example down, okay? Okay. All right, so let me see here. I heard a chat. That's right, Mikhail, it would be. Mikhail's mentioning about using an inverse to, so first thing we have to do Okay, so what we have here, let's think about what we have. So, well, we're going to have to get our hands a little dirty here to do this problem. But I mean, what you have here are vectors b1 and b2, and those form a basis for R2. Now, it's not the standard basis. Standard basis would be vectors 1, 0, and 0, 1. But nevertheless, b1 and b2 form a basis for R2. And because those basis vectors there are two of them in R2, and they're linearly independent. Similarly, vectors C1 and C2 form another basis for R2. What we want to do in part A is we want to find the change of coordinates matrix from basis B to basis C. Once we know that, okay, once we find that, then we can easily find the change of coordinates matrix from basis C to basis B. So how do we go about doing this? What's the procedure? All right, what we have to do is really to understand it, we just have to ask the right questions, and then that'll guide us to the answer. So if we look here in the solution, what I want you to look at first is the box on the right. Okay, the box on the right. This box here. So let's talk about this. Let's talk about this right here. Okay, this augmented matrix. Okay, let me go to the whiteboard real quick. So you have an augmented matrix that consists of vectors C1, C2, and vector B1. Really, what you're doing here is you're saying find values x1 and values x2 such that x1 times c1 plus x times c2 equals b1. So then the vector x1, x2, okay, and maybe what I'll do, want to be a little bit careful here, but that's fine. The vector x1, x2, in this case, is equal to the coordinate vector of b1 relative to basis C. You see what I'm saying here? If we want to find the coordinate vector of b1 relative to basis C, then this is the vector equation we have to solve, because it's the x1 and the x2 that are the coordinates. Now, similarly, if we had the augmented matrix with vectors C1, C2, and vector B2, then we're solving an augmented matrix. We're solving an augmented matrix, and that augmented matrix can be written as a vector equation this way: y1 times c1 plus y2 times c2 equals b2. Okay, so the coordinates in this case are y1 and y2. So the coordinates here y1 and y2 are the coordinate vectors of B2 relative to basis C. Because remember, basis C consists of vectors C1 and C2, right? So the change of coordinates matrix, the change of coordinates matrix from B to C, okay, we denote that change of coordinates matrix from basis B to basis C. It's just going to consist, it's going to be the matrix that consists of those two coordinate vectors. How many remember seeing this? Or, well, I want to be a little bit careful. I don't want to, I just want to keep, I mean, this is that matrix, and that matrix is what we need to go from one coordinate system to another coordinate system. So essentially what happens is then here is you have two systems of equations that you have to solve. Okay, and what we can do, you see, is we can solve those two systems simultaneously. It's sort of strange, but look how I set this up. Look how I set this up on the left. If I want to solve if I want to get the two coordinate vectors at once, I can set up this augmented matrix. You see? I mean, because finding both coordinate vectors involves solving an augmented matrix whose like the matrix A is just C1 and C2. So you can solve like you see here on the right in the box. You can solve these two systems separately if you want, but you can also solve for them at the same time. You see? So you're not repeating the row operations. Because if you solve the two systems of equations if you solve the two augmented matrices separately to get the coordinate vectors, you're going to be doing the same row operations. So why not just set it up this way and only go through it once? So what row operation do I do here? Well, I want the -4 to go away. So I'm going to use that 1 there as a pivot. I'm going to take 4 times row 1, add it to row 2, and replace row 2 by the result. Okay, next off, I don't want the 7 to be there. I'd like it to be a 1. So I'm going to take 1/7 times the second row and replace the second row by the result. And then finally, I don't want the 3 here. So I'm going to take the 1 as a pivot there, take -3 times row 2, add it to row 1, and replace row 1 by the result. And so what happens is this matrix on the left, you get the identity, and then on the right, you get your change of coordinates matrix from basis B to basis C. Do you see that? How you're like you're solving the two systems simultaneously? Well, so we'll talk about that, Mikhail. That's going to come next. But we have our change of coordinates matrix from basis B to basis C. And so that means if you take any vector, okay, in with coordinates relative to basis B, you can get the coordinates relative to basis C using that that matrix. All right, are there any questions on that? I want to make sure everybody's comfortable. Give me a thumbs up if you're feeling okay with it. And then, Mikhail, we're gonna address your what you said there in the thing. All right, wonderful, wonderful, excellent, excellent. Are there any questions? Okay. Well, let's go back to the problem here. So now we've done part A. We've done part A. And now we have to do part B. We have to do part B. Now we want to find the change of coordinate matrix from basis C to basis B. Okay, so if we had a vector with coordinates relative to basis C, what coordinates would that vector have relative to basis B? Okay, and here's how you do it. It's really quite fascinating. This is what we know, right? This is what we know, that the coordinate vector of x relative to basis C is equal to the change of coordinates matrix from basis B to C times the coordinate vector of x relative to the basis B. But what we can do, because the matrix P is invertible, has to be invertible, we can multiply by the inverse both sides. So let me just see here. If I can sort of fit it in here. So one moment. Okay, so P is invertible. So I will multiply by the inverse of that change of coordinates matrix. Both sides, naturally. Okay. Then here, this part here, you get the identity, 2 by 2 identity. And that's going to get you here. So therefore, the change of coordinates vector of the change of coordinates, the coordinate vector of x relative to the basis b would be equal to the inverse of the change of coordinates matrix from basis b to c times the coordinate vector of x relative to basis c. But it's common sense then that this inverse here, the inverse of the change of coordinates matrix from basis b to c, is namely the change of coordinates matrix from basis c to b. So the inverse of change of coordinates matrix from basis b to basis c is namely the change of coordinates matrix from basis c to basis c. I'm going to say this right. Okay, let's say it one more time. The inverse of the change of coordinates matrix from basis b to basis c will be the change of coordinates matrix from basis c to basis b. And that makes sense because the inverse multiplies the coordinate vector of x relative to the basis c and gives you the coordinates of x relative to the basis b. So, Mikhail, this is what you were getting at, right? This is what you were thinking about, I believe, right? In some of your earlier comments? No? Okay, all right. All right. Well, are there any questions on this? I mean, I think it's absolutely fascinating. I think it is, but I'm hoping you do too. Excellent, excellent. Wonderful. Jacob likes it. Mikhail likes it. I mean, coordinate systems, there's a reason we use different coordinate systems in applications. We've already seen it for crystal lattices, okay, and there are many other applications as well. So, all right, let me go ahead and stop the recording. Excellent.